On the 7th of November. Yesterday was the last day for complaining or requesting a makeup, so none anymore. The exam duration is 1 hour and a half. We don't have a class 8 a.m. on the 7th of November. I'm gonna hold a help session by Monday, the 5th of November at 6 p.m. ISB 221. So from now, from this minute after the class, if you have any question from any of the practice exams, just send me the number of the question, which exam it is, so that I can discuss it with you during this help session, if you're coming to the help session. So now we're done from this, and this should be done. If you are registered with the Disability Services, you should already be contacting them. So what's exactly in the exam? All in chapter 5, all in chapter 6, and chapter 7, the lecture from Wednesday. And today's lecture, part of today's lecture, I'm going to tell you when is the end of the lecture that is included in the exam. What's exactly in this lecture that is included in the exam. And the slide 16 on are not included in the exam. So it's still slide 16. So from slide 1 to slide 15, all included in the exam of today's lecture. 16 on is not included. Okay? So, the practice exam and the info page are already on Moodle. If you'd like to know which equation I'm going to give you, it's already there. It's called Information Page Exam 2 in the practice exam folder. Now let's go back to chapter 7. So the last time we talked about electronic configuration, and just let me remind you that we said the way that we fill the subshell is 1S, 2S, 2P, 3S, 3P, 4S, 3D, and definitely after that 4P. So this is the way how we fill them. We said that each orbital can maximum accommodate 2 electrons. If we are putting 2 electrons in the same orbital, they must have opposite spins. S can maximum accommodate 2 electrons. P, 6 electrons, because P has 3 orbitals. D can maximum accommodate 10 electrons. And F can maximum accommodate 14 electrons. The last time we talked about the transition metals, and they are the D block, where we fill the 4S before the 3D. And this is definitely that's not a transition metal. Calcium is not a transition metal. So these are the electronic configuration of the group 4 transition metals. Those are the ones that you're responsible for. The last time we emphasized on the fact that copper and the chromium are both an exception, in which we promote the 1 electron from S to the D. In this configuration, they put the 3D before the 4S. Either way is okay. If you put the 4S before the 3D, it's also okay. It's an accepted configuration. So you have to get used to the idea that both of them are used. So this is the electronic configuration of all the transition metals that you're responsible for. Now, group 5 transition metals, there are more exceptions, and it's not in the same group. This is why I usually wouldn't talk about group 5, group 6 transition metals, and definitely not the lanthanides and actinides. Okay, so let's go back to nitrogen. So if I write the electronic configuration of nitrogen, it's going to be 1s2, 2s2, 2p, 2p3. So again, the largest number of n represents the period. So n is in period 2, and the group 5, which is I add the number of electrons on the valence shell. We call this the core electron. Those are the valence electrons. Those that are in the highest n. Remember that the number before the subshell is the n, represents the shell, the n. So this number in here, that represents n equal to. Okay? Now, if I write the box notation for nitrogen, according to Hunt's rule, put those electrons each in a box, each in an orbital, and they're gonna have the same spin, the same parallel to each other. Now, the material that have unpaired electrons, which is the case in here, we have 3 unpaired electrons, is paramagnetic. And we're gonna talk in a minute, what does that mean? What does paramagnetic mean? So, the element that have unpaired electrons, it's called paramagnetic. Now let's look at the beryllium configuration. It is 1s2, 2s2. If I draw the box notation, we find that all the electrons in beryllium are paired. All electrons are paired. So beryllium is diamagnetic. And we're going to talk what's the difference between the two. So, if we have at least one unpaired electron, the material or the element is called paramagnetic. And from the name, that means it has a certain effect with the magnet that we're going to talk about in a minute. If all the electrons are paired, the material or the element is called diamagnetic. Okay, so let's start with the paramagnetic. What are the characteristics of a paramagnetic atom or element? So a paramagnetic element or atom, it has those electrons, one unpaired electron. When I put it in a magnetic field, those electrons will be aligned, the same as in here. So here it is paramagnetic. So when I put the magnetic field, it's all aligned, and when it is all aligned, it's called ferromagnetic. Now, paramagnetic elements or compounds, they usually get attracted to the magnet. So if I tell you now this material gets attracted to the magnet, you know for sure that in its electronic configuration there is at least one unpaired electron. Okay? So that's the definition of paramagnetic material. Paramagnetic material get attracted to the magnet, and the reason behind it that it will have at least one unpaired electron, that when it is in a magnetic field, those align up, all these electrons align up, and now it gets attracted by the magnet. Now, let's see what's the definition of diamagnetic. We know that diamagnetic is the material that has all its electrons paired, which is in this way. Now, even if I put it in a magnetic field, it's not going to be able to change because the electrons in the same orbital must have opposite spins. So this substance, which is diamagnetic, is usually repelled by the magnet. So paramagnetic, attracted by the magnet, diamagnetic, repelled by the magnet. Okay? And you need to know those two definitions and what exactly that means according to the magnetic property of the material. An example of that, I'm going to show you two examples of a magnetic and paramagnetic material. So here we have a magnet in there, and I have two liquids. One is oxygen, gas, oxygen liquid, liquid oxygen, and liquid nitrogen. I just want you to be aware that in both of those materials, I have N2 and O2. I don't have nitrogen and oxygen. Okay? So I'm not talking here about nitrogen and oxygen. I'm talking about the molecule nitrogen and the molecule oxygen. Okay? So let's go back. So the first one, they are adding the liquid. The liquid clearly doesn't stay. It just passes through the magnet. Now for the second one, the liquid is paramagnetic and it's get attracted between the magnet, the two magnets. So the second liquid, I'm going to just repeat that. So the second liquid is the paramagnetic one. Why? Because it gets attracted to the magnet. The first one is just passed by, even it's just kind of spread as it goes because it is diamagnetic and it's repelled by the magnet. The second liquid, as you can see, it's getting in between and gets attracted to the magnet. So it is paramagnetic. Okay? Another example is the one in here. We have iron oxide, and we're gonna figure today that iron is 3 plus. That means when iron loses 3 electrons, it's gonna be paramagnetic, and this is why this iron oxide, this is a magnet, it is attracted by the magnet. Okay? Now, we learned how to do the electronic configuration of atoms as they are from the periodic table. Now, what about ions? What about cations? What about anions? How we figure out their configuration. So now we're going to talk about the electronic configuration of ions. And I'm going to start it directly with eye clicking. So what is the electronic configuration of Na+, knowing that Na has 11 electrons? And think about whether Na+ is para or diamagnetic. I'm going to stop it at 1 point. Okay. I'm going to stop it right here and check what you think. So I have 65% for B and 32% for A. And B is the right answer. Okay, the way that we handle the electronic configuration of ion, whether it is cation or anion, is first we look to the electronic configuration. So Na11, the electronic configuration of that is 1s2, 2s2, 2p6, that's 4, 6, and 3s1. This is the electronic configuration of sodium as a neutral element. But what does sodium plus mean? What does Na plus mean? Did the element lose or gain electrons? From chapter 3, oxidation reduction. Lost. Very good. So now instead of 11 electrons, it's going to have 10 electrons. So it's going to be 1s2, 2s2, 2p6, and usually, definitely, we're going to lose the electron from the outermost shell, from the highest, not the valence electron. And this is why we take off 1 electron from here. So it is 3s0, that means it is empty now, and this is the electronic configuration of sodium plus. Now, the second thing, is sodium plus para or diamagnetic? Is it para or diamagnetic? Because if we look to the box notation in here, I have 6 electrons, so all of them are paired, therefore it is diamagnetic. Okay, is sodium as a neutral element dia or para? Paramagnetic. And that's tell you that if the element is paramagnetic, that doesn't mean that the atom, if is paramagnetic, if the atom is paramagnetic, that doesn't mean the ion is paramagnetic. Okay? Now, can you look to the sodium, look at the sodium plus electronic configuration. Write the Nobel notation of that. Okay, and I'm hearing somebody saying it's exactly a neon. That if we look to the noble gas notation, it's neon. Does that surprise you? It shouldn't, because everything in this periodic table lose or gain electron to look like a noble gas, electronically like a noble gas. And this is what I was talking about in the very early chapters when I say, oh, only group 1 lose 1 electron to look like a noble gas. This is what it is. It's in the electronic configuration, it looks like a noble gas. Only group 2 loses 2 electrons, and this is why we say calcium is 2+, magnesium exists as 2+. Because all group 2, if they lose 2 electrons, they're gonna look like the noble gas in the period before them, in the row before them. Now the same for fluorine, or chlorine, or bromine, all of them, they gain 1 electron to look like the noble gas in the same row. The same for group 6A, all of them, they gain 2 electrons to look like the noble gas, electronically like the noble gas in the same row. Okay? So let's do one more on the electronic configuration of ions. So what is the electronic configuration of F-? And think whether F- is paramagnetic. The same question that I asked on the previous one. And again, I'm going to stop it at 120. Okay. So I'm going to stop it right here and check what you say. And I have 92% for CC is the right answer. So again, we start with the neutral atom. It is 1s2, 2s2, 2p. So 4, 5. But F-, that implies it gained 1 electron. So I'm going to add 1 electron to the outermost shell. So 2p6. So now this is diamagnetic. Okay, and it has exactly the noble gas notation of neon, which makes sense. Okay. Let's go further. What about Fe2+? What is the electronic configuration of Fe2+?
It's because this is the straight up regular iron. It's 2 plus 6 leading 2 electrons. It moves it from the highest shell 4 is way further away from the nucleus than 3D. So that's the electrons.
And we're going to stop it at 1. Okay. So I'm stopping right here and check what you think. And I have C at 75%. C is the wrong answer. D is the right answer. Okay, let's see why. Okay, so first Fe. So it's argon 4s2, that's 23d6. So this is the electronic configuration of iron For iron, 2 plus, that means we lost 2 electrons. Usually we're gonna lose the 2 electrons from the outmost shell. Okay, let's see, which one is the highest shell? Is it 4s or 3d? 4s. So we're gonna aim for transition metals. That's the rule of thumb. For transition metals, you gain the loss or gain of electrons first starts in NS. In this case, it is 4s, but in any NS, then N minus 1d, the d before it. So this is why some books put 3d before the 4s. Although we fill the 4s before the 3d, when we lose electrons, we lose from the 4s in the transition metal before the 3d. And this is why most of you chose C, and I totally understand because I didn't explain this idea before. So it's going to be argon 3d6. Now, even we don't put it as 4s0, but in this case, I put it 4s0 just to show you that the electrons are lost from 4s, but usually this is how we put it when we lose electrons from 4s, it's argon 3d6, okay? And this is why some books put the 3d before the 4s, because they think it's gonna make it easier for you to understand that you're gonna lose electrons from the 4s rather than 3d. So you fill the 4s, when you're filling the electronic configuration, you fill 4s before 3d. When you're losing electrons, when transition metal lose electrons, they lose it from 4s rather than the 3d. Does that make sense? You have to keep that in mind, okay? Now, is Fe2 plus para or dia? So again, I'm gonna draw the box notation. D have 5 orbitals, 1, 2, 3, 1, 2, 3, 4, 5. According to Hunt's rule, I'm gonna put the electrons each alone. 1, 2, 3, 4, 5, 6. So I have 1, 2, 3, 4 unpaired electrons. Therefore it is paramagnetic. For a paramagnetic, I need at least 1 unpaired electron. In this case, I have 4 unpaired electrons. So to know whether it is paramagnetic or dia, you need to draw the box notation. Remember, the p subshell has 3 orbitals, the d subshell has 5 orbitals, the f has 7 orbitals. Okay? So let's do more on this. So B is the right answer. Okay, what about copper 2 plus? Again, I'm going to stop it at 120. So each one of those eye clickers, I'm going to stop them at 120. Okay. Yeah, I'm going to stop it right here and check what to use next. And I have B to be the highest, and yes, B is the right answer. So first of all, copper 29. Whenever you hear copper or chromium, both of them, they have exception or they are exception. So it's going to be argon 4s1 3d10. This is the copper. This is the electronic configuration of copper, and it's with the chromium. Both of them are exceptions. Now what about copper? 2 plus. That means the copper lost 2 electrons. So the first electron gonna go from the 4s. So I have no 4s, and then 1 electron from the 3d. So it's gonna be 3d9. So this is the electronic configuration of copper 2 plus. Is it para or diamagnetic? It's para. That's right. So again, I'm gonna draw the box notation 1, 2, 3, 4, 5. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has at least 1 unpaired electron, so it is para. Okay. I think this is the last. No, we still have some. Okay. Let's do more. So, what 2 plus ion has the following electronic configuration? So I'm going to stop it right here and check what you think. C for 74%. C is the right answer. So in this equation, you have 2 ways to solve it. The first way is what is the 2 plus ion, what 2 plus ion has the following electronic configuration. That means this is the configuration of something that already lost 2 electrons. That means if I want to know the electronic configuration of the neutral atom, I would add 2 electrons to this configuration. So if I add 2 electrons to this configuration, and I count the number of electrons, 18 electrons for argon, plus 10, plus 2, that ends up to exactly to the zinc electronic configuration. So this is why it is 2 plus. Okay, the other way to do it is to write the electronic configuration of all the choices, and that's time consuming. Usually the easiest way is to look, if it is 2 plus ion, that means it already lost 2 electrons. If you add 2 electrons, so it is the opposite of the question, what is the electronic configuration of sodium plus? So you first try the electronic configuration of sodium, then you take 1 electron. In this case, you have the electronic configuration of the anion, of the cation, and then you're gonna add to it 2 electrons. So zinc 2 plus is the right answer for this one. Okay, let's do some more. Okay. For which of the following atom is the 2 plus ion paramagnetic? I'm gonna give you 2 minutes for this one because we need to write the electronic configuration. That's gonna take a little bit more time.
It's under your chair.
2 minutes and check what you. Okay, I have B at the highest percentage. Let's see. So first zinc 2 plus. I know. Okay, let me do it slowly. So zinc 30. So it's argon 4s2 3d10. Now for zinc 2 plus 2 electrons, it's going to go from the 4s, not from the 3. So 3d10, if I write the box notation, 5, I have 10 electrons, so it is diamagnetic. Okay, manganese 25, so it is argon 4s2 3d5. I'm gonna lose 2 plus, I'm gonna lose them from the 4s, so clearly it is paramagnetic. Because I have 1, 2, 3, 4, 5, so paramagnetic. Okay, silicon 14, so it is 1s2, 2s2, 2p6, 3s2, 3p. So that's 10, 14. So if you lose 2 electrons, it's going to lose it from the atoms to shell. 2p6, 3s2, and it is diamagnetic. Okay? So definitely B is the right answer. Okay? Okay. And sorry, that's going to be A. This is your choice B. This is your choice C. So which of the following atoms is paramagnetic? Try to do it without writing the electronic configuration. And this is why this question is here. Because I want you to think about it without writing the electronic configuration. Okay, so let's right here and check what you think. Okay. So I have C, the highest C is the right answer. So the way, if I'm asking you about elements being neutral, that means they didn't lose or gain any electrons, it is easy to figure it out by just looking at the periodic table without doing the electronic configuration. Remember that all those in group 1 have NS1 as electronic configuration. So all group 1 as atoms, as neutral atoms, not when they lose or gain electrons, they are all paramagnetic. Why? Because they have NS1, that means they have at least one unpaired electron, so paramagnetic. Now, group 2, we said that all of these have NS2 as a valence electron. That means NS2, we have one orbital, so those are paired. So all of the group 2 as a neutral atom, not when they lose or gain, they are diamagnetic. Okay, let's go to this part of the periodic table. For this one, it's NS2, NP1. So is it para or dia? Paramagnetic, because we have one electron in the P. So only group 3 as neutral atoms, they are paramagnetic. paramagnetic. What about group 4A? It is NS2, NP2. So again, it's para. This group it's NS2, NP3. It's para. What about this? NS2, NP4. It's also para. And this one definitely is para. While for 8, it is I'm gonna write it down here. For all this group, it is NS2, NP6. So it is diamagnetic. So in such kind of questions, if I'm asking about the neutral one, most probably I'm gonna give you 5 choices. If you begin writing the 5 electronic configurations, that's at least 10 minutes. You can just figure it out by looking to the periodic table. Put them, as I did in here, circle them, and then from there you can figure out if they are in neutral. You can look, oh, group 2A, all of them are dia. Group 6, all of them are para. Group 8, all of them are dia, and so on. So you can do it without writing the electronic configuration. Okay? And this is the last slide that is included in the exam. Anything that I'm going to talk about from here on is not included in the exam. Okay. Now that we're done from the electronic configuration and all of these stuff, what we're going to talk about now, how the electronic configuration and where is the atom in the periodic table going to affect other properties like the radius, like the ionization energy, the electron affinity, the electron negativity of the material. So, for atomic radius, as we said before when we were talking about Schrödinger equation, that the orbital is mainly a probability. We don't have a definitive answer where is the electron. We only have a probability. And because of that, the way that we calculate the radius is we take a molecule, especially for nonmetals. For example, if I want to calculate the radius of Cl as an atom, I take Cl2, which is a compound of Cl, and I measure the distance between the 2 nuclei, and from there I divide it by 2 and know the radius of Cl. Then I take it in another compound and I do the calculation. This is why all the radiuses the radii that you're gonna see in tables, they're gonna put a star and say it's an average radius. Why? Because there is no way that we can measure the radius by an instrument as we measure, for example, how many inches is this. This is why always you're gonna see in tables that the radius you have an average. So for nonmetals, we usually just take it in compounds and calculate the distance between the 2 nuclei. In metals, we take the crystal lattice and we measure it depending on the crystal lattice. Now you don't have to know neither how to calculate that or this. This is just to tell you because later on you're gonna hear about it in Chem 121 about the crystal lattices, and you're gonna hear about how to calculate the radiuses by other methods. This is why I'm just bringing the issue. Yet, what we're gonna learn is by looking to the periodic table to estimate which radius is higher than the other one as atoms. This is what we're gonna do next. So, as we go down the group, what is your expectation? Would the radius increase or decrease of the atom? Let's take group 1. If I go all the way down from hydrogen to potassium to Fr, which one gonna have the biggest radius? So as we go down the group, remember we're adding electron because unequal 1, that means the electrons are in shell equal 1. Unequal 2, which is the second period, we're adding electron to the second shell. Unequal 3, unequal 4. So definitely the electrons are getting far away from the nucleus, and that's make the radius increase. So the radius increase as we go in a group, down in a group, and that's a rule of thumb. It works for every group in the periodic table. As you go down the group, the radius is gonna increase. So in other words, if I ask you which have a bigger radius, fluorine or chlorine? Chlorine definitely gonna have a higher radius or a bigger radius than fluorine. Okay? And the same applies for all the groups, every group in the periodic table. So the radius increases as we go down the group. Okay, what about if we go in the same period? So if I go from sodium to Cl, the radius will decrease. So if I go in the same group in the same period, and this is period 3, as I go from sodium to magnesium to aluminum, the radius will decrease. So that means the radius increases this way. Okay? Now the reason behind that the radius decrease as I go in the same period is that the number of protons inside the nucleus, the effectiveness of the number of protons inside the nucleus is increasing. And we refer to that by Z star. That means the effective nuclear charge. I'm not gonna go talk a lot about the effective nuclear charge. Just think about it that the effect of the protons on the electron is increasing as we go from through the period, and that's make the electron get more attracted to the nucleus and make the radius smaller as we go in the same group. Okay. So the summary of that if I go down in a group, the radius will decrease, the radius will increase, and as I go this way, the radius will increase. So in other words, the atomic radii increase this way and this way. Okay? So if I'm asking you about the radius of the element in here and in here, the one in here is gonna have a bigger radius than the other. Okay? Does that make sense? Okay, so okay, so this is for the main groups. That means not the transition metal. This applies to everything. Now let's see what about the transition metal. Do they have the same properties as radii? So again, for transition metal, the radius as we go in the same period, it decreases. The radius decreases. But there are two exceptions, which is when we get to the carbon and the zinc, the radius increases slightly increase when we come to the copper and zinc. The reason behind it, because both copper and zinc, they have for the zinc, as we saw a minute ago, it's argon, for S2, 3D10, it have a full shell, a full orbital, and all its electrons are paired, and they begin repelling each other, and that causes a slight increase in the radius. The same for the copper. So that implies that rule that the radius increase this way and that way applies, except with an exception between nickel and copper. Copper has a slightly higher radius than nickel, and zinc has a slightly higher radius than copper. Okay? See. Okay, let's do an eye clicker about this to see if you get the idea. This is the Cl, this is the sulfur, and this is the selenium. So those are the elements that we're talking about. The one that I circled in red. So I'm gonna stop it right here and check what you think. And I have 80% for C. C is the right answer. Very good. Okay, so again, to solve such kind of question, label them in the periodic table, what I'm asking you about, and always think that the radius is increasing this way and as you go this way. That implies that AS has definitely a higher radius than the sulfur, than sulfur and chlorine. Why? Because they are in the period before. Okay, so that tells me AS has a higher radius than sulfur and chlorine. But I know that the radius increases this way. That means SE, that STT has a higher radius than SE, has a bigger radius than SE. Yet I have sulfur and chlorine. I know that sulfur has a higher radius or bigger radius than Cl because usually the radius increases this way. So that makes C the right answer. Okay? Now, we're gonna move now from the atomic radii, and usually we teach you those because you're gonna use them later on. When you go to other chemistry courses, they're gonna just tell you, oh, this is more acidic because this one has a higher radius or smaller radius. This is why we're teaching you those. Now we're gonna go to another property that is coupled with the periodic table. That means there is a trend in the periodic table, which is the ionization energy. So what is ionization energy? By definition, ionization energy is the energy required to remove an electron from an atom in the gas phase. And I'm gonna highlight the gas phase, okay? Now, the ionization energy is always positive. When the energy is positive, what does that mean? Is it an endothermic or exothermic reaction? When Q is positive, endo or exo? Endo. That means I need energy to take the electrons out of the atom, and that makes sense. Definitely I need energy to just overcome the interaction, the force between the protons and the electrons. So the ionization energy is always positive. It's always an endothermic. We need energy to take an electron. Now, I'm going to insert in here. So if I have magnesium in the gas phase minus 1 electron to give me Mg plus, this is the first ionization energy, and I need 738 kilojoule per mole. So again, both of the magnesium and its ion must be in the gas phase. This is the definition of ionization energy. Must be in the gas phase. So this is the first ionization energy. Now the second ionization energy is to take the Mg plus, the first ion, in the gas phase minus 1 electron to give Mg2 plus. So the second ionization energy is always higher than the first ionization energy. Okay? And definitely both of those are in the gas phase. So by definition, if I ask you to write the ionization energy of any element in the periodic table, it is taking it from the gas phase to the ion in the gas phase. Okay? This is the definition of ionization energy. Okay? Now, if I ask you about the second ionization energy, it's taking the ion with plus to 2 plus. And I'm going to stop right here, and I'll see you Monday. Enjoy your weekend. Have a great one.